Hello Year 12 and welcome to our next video here on graphs and equations. We're looking today at vertical and horizontal asymptotes. We spoke about vertical asymptotes briefly in the last video, and they generally occur when I have some sort of algebraic fraction and the denominator includes a variable, and it's where the denominator is equal to 0. So we need to check those out. Vertical asymptotes, where the denominator is equal to 0. Horizontal asymptotes, we haven't necessarily come across so much before. And that's perhaps because we've been mostly dealing with polynomials that tend towards infinity or negative infinity. Right? They tend to keep getting bigger or smaller as x moves to the right or the left of the number line. For very large or very small values of x, our function for a polynomial typically becomes very large or very small. However, we're going to look at things like perhaps a rational function where I have a polynomial divided by a polynomial, and they can get a bit more interesting there. Some other functions that we have learned about that have horizontal asymptotes are logarithmic functions. And for that matter, exponential functions might have a horizontal asymptote as well. Logarithmic functions, not necessarily actually, sorry for the red herring there. Exponentials typically too, logarithmics might. Now, the way we're going to test for horizontal asymptotes is by considering what happens when x gets very large and very small. We've got a little trick up our sleeve for doing that. Now, we're going to jump straight into this example. I've got this function here, negative 2 over x plus 2, and we're asked to write the domain of this using both notations. Well, our domain is going to be all values of x except for x cannot be negative 2. So I could say, I might say x does not equal negative 2. That seems pretty good to me. Or I could say negative infinity to negative 2, but not including negative 2, or negative 2, but not including negative 2, up to positive infinity. Okay, that'll do us. That's our domain using two different notations. Now, odd, even, or neither. To do this, we consider, I'm going to need a bit more room, I'm going to have to skip down the bottom here, b. Consider function of negative x, and I get negative 2 over negative x plus 2, and that is neither my original function, nor is it the original function multiplied by negative 1. It's not the negative of the original function. No, so that's neither odd nor even. What about C? What are we asked to do here? Find any zeros and discontinuities, construct a table of signs. Well, we determine there that I have a discontinuity when x equals negative 2. Is there any way for this function to be equal to 0? Given my numerator is a constant, is 2 or negative 2, whichever way you want to interpret that, there's nothing I can divide a constant by to make it equal to 0. Okay, so this function does not have any x-intercepts. So I have an asymptote, vertical asymptote. Oops. At x equals negative 2, and that's all. I don't have any zeros. So when I draw up my table of signs, x and sine, I need to consider what happens at negative 2 and just a little bit either side. So let's say negative 3, and I could say negative 1, but I much prefer to use 0 where I can. Sorry about the noise there. So if x equals negative 2, it's undefined. Don't know what's going on there. What if x is negative 3? Well, my function becomes, my denominator is negative 3 plus 2, so it's negative 1. It's negative 2 over negative 1 is positive. And if x equals 0, I get negative 2 over 2 is negative 1 is a negative number. So my function is positive to the left of negative 2 and negative to the right of negative 2. Let's see. Find the vertical asymptote, describe its behaviour near it. Well, I think we've done close enough there with D. Vertical asymptote does ask us to describe it, so we better do that. Vertical asymptote at x equals negative 2, positive to the left, negative to the right. It's D. Now E. Find the horizontal asymptote. Describe its behaviour near it. We're going to learn some more techniques to do this soon, but right now let's just consider what happens when x gets very large. I'll get negative 2 over a very large number, which will become very close to 0. Okay? If I do 2 divided by a large number, it approaches 0. Similarly, 2 divided by a very large or a very small number, a very negative number, the plus 2 is not going to make much difference. It's still going to be very negative as I approach negative infinity. And so again, I'm going to approach 0. So horizontal asymptote y equals 0 at left and right. Rightio. That's enough. Now we can sketch the curve. Consider all the things that we have going on here. Let's draw our axes. X here and Y here. The x-axis, remember, is an asymptote. And I have another asymptote at x equals negative 2. It is negative to the right of that. Okay, so it's going to do this. And positive to the left. So it does that. There's our sketch. The one more thing I could find the Y-Intercept. If x equals 0, I get negative 2 over 2. That's negative 1, so I guess I could label that if I really want to. That's probably a good thing for a sketch, but that's it. Now, we investigated that horizontal asymptote just sort of by inspection. Sometimes, however, we need to take a bit more of a formal approach to understand what's going on. And the way we're going to do this, where we have a rational fraction, where I have a polynomial on the top and bottom of a fraction, I'm going to divide every term in both polynomial by the highest power of x. Now, as x becomes very large, or very small, by which I mean very negative, dividing a constant by a very large or very small number approaches 0. So I will only be interested in the highest powers of x. Show you how this works. So what I want to find, first of all, the limit as x approaches infinity here of x squared minus 1 over 2x squared plus 5x plus 3. What happens when x gets very large? That's essentially what that means. Well, we're going to divide everything by x squared. So this gives me x squared over x squared minus 1 over, I should still put the limit in there, equals the limit as x approaches infinity of x squared over x squared minus 1 over x squared over 2x squared over x squared plus 5x over x squared plus 3 over x squared, right, which will be the limit as x approaches infinity of 1 minus 1 over x squared over 2 plus 5 over x plus 3 over x squared, just cancelling some of those x's, Now, as x gets very large, 1 remains 1. 1 over x squared becomes 0. 2 remains 2. 5 over x becomes 0, or approaches 0, and 3 over x squared also approaches 0. So I'm left with 1 over 2. Okay, so as x becomes very large for that function, it approaches, not infinity, not negative infinity, not 0, it approaches 1/2. Now, that will also be the case in this style of function for negative infinity. Okay, now I don't need to go back because this is what we call a rational function, polynomial top and bottom. Okay, I'm again going to divide everything by x squared, and whether I'm dividing a constant by infinity or negative infinity, either way they approach 0. Okay, so my horizontal asymptote there is 1/2. Now it does say, sketch each function showing any zeros and asymptotes. Right, all I've found there is the horizontal asymptote. I should still sketch this as, I've got to find roots here. Okay. Now, if my function here, x squared minus 1 is x plus 1, x minus 1. And my denominator is, this must be 2x plus 3, x plus 1. So, some interesting things going on here. I shouldn't cancel the x plus 1s. Okay, if mostly when I'm sketching this, I guess I sort of can. However, my function is undefined when x equals either negative 1.5, negative 3 over 2, or x equals negative 1. So x does not equal negative 3 over 2, or x does not equal negative 1. When x equals negative 1, then my function will be equal to 0. My numerator becomes 0, my denominator isn't. Now, x equals 1 isn't a 0 of this. Even though the numerator is 0, it cancels with the denominator. So when I have a 0 in the numerator and denominator, I have a discontinuity. Okay, discontinuity at x equals negative 1. I'm going to have an asymptote, vertical asymptote, at x equals negative 3 over 2. So, vertical asymptote, discontinuity, a horizontal asymptote. We should from here draw up a table of signs. Now my important values here are when x equals negative 3 over 2, negative 1, and 1. And I need to choose numbers either side of that. So greater than 1 is 2, between negative 1 and 1 is 0, between 1 and negative 3 over 2, let's say negative, let's say 5 over 4, negative 1.25, it's between negative 1 and negative 1.5, and then something less than negative 3 over 2, let's say negative 2. Right, so quite a big table of signs this time because it's quite a complicated function. Righto. So what happens when x equals negative 2? My denominator is positive. Negative 2 plus 1 is negative 1, negative 2 minus 1, negative times a negative, the numerator is positive. My denominator, negative 4 plus 3 is negative 1. Negative 2 plus 1 is negative 1. Negative times a negative is positive, so it's positive divided by positive. So my sign is positive when x is less than negative 3 over 2. Now, negative 3 over 2, undefined, I would be dividing by 0. Negative 5 over 4. Negative 5 over 4 plus 1 is negative. Negative 5 over 4 minus 1 is also negative. Negative times negative. My numerator is positive. My denominator, 2 lots of negative 5 over 4 is negative 5 over 2. Right, negative 5 over 2 is negative 2.5 plus 3 is positive. Negative 5 over 4 plus 1 is still negative. Positive times a negative is a negative. My numerator is positive. My denominator is negative. That means that the whole function is negative. At negative 1, undefined, can't divide by 0. It's an easy one. At 0, I get 1 by negative 1. Negative denominator, negative numerator. 3 times 1, a positive denominator. Negative divided by a positive is a negative. At x equals 1, my denominator is positive, my numerator is 0. And at x equals 2, I get positive times a positive over positive times a positive is positive. Okay, bringing all of those things together, we need a sketch. Boy, am I running out of space. You can see these are long, complicated questions. Righto. So, from here, I have a vertical asymptote at, what did I say? My vertical asymptote was negative 3 over 2. I have a horizontal asymptote is at 1/2. Y equals 1 over 2. Scroll down here. X equals negative 3 over 2. Right. I have a 0 of my function. I'm going to cross the x-axis here at 1. Okay. And I've just got to keep in mind I have a discontinuity at negative 1. So, what happens here is my function, I have a horizontal asymptote. And then here at 1, I get a little open circle before I head down that way. Okay, so it's positive for everything greater than 1. Between 1 and negative 1, it's negative, then a discontinuity. Between my discontinuity there and negative 3 over 2, I have, I'm still negative. And anything less than negative 3 over 2 is positive again. So my vertical asymptote and my horizontal asymptote. Okay, so that's my function there. It probably should be a bit curvier. I could find the Y-intercept fairly easily, I suppose. Let x equals 0, and I get negative 1 over 3. So that's negative 1 over 3. Rightio, that'll do us. I could find the coordinates of that discontinuity too, but look, I think that's going to do us. I think that's pretty good. Rightio, now one more case here. We talked about polynomial in the numerator and denominator. What about an exponential? The important thing to remember here, exponentials as they approach infinity, as x approaches infinity, 2 to the power of infinity is very large. But 2 to the power of negative infinity isn't very small. Well, doesn't approach negative infinity. Right, 2 to the negative infinity is like 1 over 2 to a very large number, which is approaching 0. Rightio. So what we aim to do here is, to divide everything by our exponential. Rightio. So consider this, the limit as 2 to the x plus 1 over 2 to the x minus 1. Oh, Why have I written that like that? No idea. The limit as x approaches, let's do this, as x approaches infinity of 2 to the x, oops, oh, that's not 2 to the x, of 2 to the x plus 1 over 2 to the x minus 1, right, is the limit as x approaches infinity of, let's say, 2 to the x over 2 to the x plus 1 over 2 to the x over 2 to the x over 2 to the x minus 1 over 2 to the x. Okay, this is the limit as x approaches infinity of 1 plus 1 over 2 to the x over 1 minus 1 over 2 to the x. Now, as x gets very large, 1 over 2 to the x becomes 0. So I get 1 over 1. So as x gets very large, this function approaches 1. What about when x gets very small? Now, with exponentials, it's a different story. This time I'm going to say the limit as x approaches negative infinity of 2 to the x plus 1 over 2 to the x minus 1. And this time I'm just going to leave it be, because 2 to the power of negative infinity approaches 0. Okay, that's 1 over 2 to the infinity. So I get 1 over negative 1, which is equal to negative 1. So this approaches 1 on the right and negative 1 on the left. What about, right, going through all of these things, we should have checked the yeah, I've been talking about horizontal asymptotes. We should work through this a bit more systematically. The domain, well, I can't have a denominator of 0. That means that x does not equal 0. Okay, let's just rule this part off here. X does not equal 0 because 2 to the 0 would be 1, 1 minus 1 would be 0, would be a problem. So, doesn't occur at x equals 0. Now, I have a 0 when 2 to the x plus 1, 2 to the x plus 1 is equal to 0. Can 2 to the power of x equal negative 1? Can 2 to the x plus 1 equal 0? It can't, because I can't change the sign of that base. So it doesn't have, right, it doesn't have any, it doesn't have any zeros, okay? It never crosses the x-axis. So, all we need to do now is a quick table of signs, so x and the sign of my function. And I need to check what happens either side of 0. 0, negative 1 and 1. Right, at x equals 0, my numerator is 2 to the 0 plus 1, right, is 2. My denominator is 2 to the 0 is 1 minus 1, so undefined. If x is negative 1, 2 to the negative 1 is a half plus 1, positive. 2 to the negative 1 is a half minus 1 is negative. Positive divided by negative is negative. And if x was equal to 1, I'd have 2 plus 1 is 3. Over 2 minus 1 would be 1, so I just get positive 3. So here we go. What have we got going on? We have a vertical asymptote at x equals 0. We have a horizontal asymptote on the right of 1 and on the left of negative 1. X, Y, okay, so asymptote here, a 1 here, Y equals 1, another one here, Y equals negative 1, so it's positive here on the right, and it's negative here on the left. Rightio, that is it. That's been a bit of a killer, really. There's a lot to take in there, a lot to do. Each of these questions takes a long time. Now, we're only talking about vertical and horizontal asymptotes, but once we start applying those to sketching graphs, there are a lot of steps to go through and quite a lot of work. If anything there doesn't quite make sense, you know what to do. Make sure you jot it down so you don't forget and ask me in class. See you there, guys.